In the previous lecture, we saw how the quantum Zeno effect can hinder the evolution of a qubit. In this lecture, we construct quantum states of qubit pairs from single qubit building blocks. So let me just denote the eigenkets of the Z operator by 0 and 1, so they would be represented by the 1, 0 and the 0, 1 column. And you can see if you apply Z to this ket, so essentially this matrix applied to this column, it gives the same column back with a factor of 1. And if we apply this matrix to this column, we get the column back, but multiplied by -1. Which is to say that the Z operator is the 0, 0 ket bra minus the 1, 1 ket bra. We apply Z to the 0 ket, then we get the 0 ket back. We apply Z to the 1 ket, we get the 1 ket back, but with a minus sign. And of course the sum of the two, the 0, 0 ket bra plus the 1, 1 ket bra, that's the identity operator for the qubit. And then we have the x and the y, and since the x, well, if we look at this matrix representation, well, we can just work it out. So we have this basis of 0, 1. Here we have the matrix 0, 1, 1, 0, and then we have the column of 0 and 1 bras. And so multiplying this out gives us the 0, 1 ket bra from here, here, and here, plus the 1, 0 ket bra from here, here, and here. And we repeat that for y. So here we have 0, 1, and here we have the matrix that we have just written down over here. So we just copy that, and we have the 0, 1 column of bras. And now we have the 0 minus I1, so we have the 0 minus I1 ket bra, and we have the 1 I0 ket bra, 1 I0 ket bra. So these are the operators x and y. And now let me note that if we combine 1 and z into 1 plus z and take half of that, well, as you can see, this just adds these terms, these two cancel, and then we divide by 2, so we get the 0, 0 ket bra, and that is just a matrix that looks like this. So it's this column multiplied by its adjoint row. And if I have the half 1 minus z combination, then now I'm subtracting z from the identity, so these two terms cancel and these double, and I get 1, 1 after dividing by 2, and that's the matrix that I would obtain by multiplying this column by its adjoint row. And finally, if I do something similar for x and y, I have the x plus iy combination divided by 2. All right, so I multiply y by I. This turns this negative I into 1 and this I into -1. So these two terms cancel in the addition, and these two add up, and I get the 0, 1 ket bra. And so now this is this column multiplied by the adjoint row of this column. And so that would be the 0, 1, 0, 0 matrix. And if I have the half x minus iy combination, then that would be 1, 0, because now if I multiply -I, then this would be -1, and this gives 0. And this I times -I will be +1. Added to this gives me twice this term. I divide by 2, and that is the matrix that looks like this, which I obtain by multiplying this column by the row that is adjoined to this column. So as you can see, the ones are in all the 4 different places of the 2 by 2 matrix, so this will be useful in what we are doing next. So now let's take the next step and look at 2 qubits. So this is all about a single qubit, but now we have a second qubit. And then the basic kets would be tensor products of kets. So this would be for the first qubit, for the second qubit, and for this we can just write a double zero. And for the 0, 1 tensor product, we will get the 0, 1 state, and so forth. For the 1, 0 tensor product, we have the 1, 0 ket, and for the 1, 1 tensor product, well, that would be the ket labeled by 1 and 1. And so those are the basic ingredients, and now if we have two of those qubits, then there will be an x for the first qubit, a y for the first qubit, a z for the first qubit, an x for the second qubit, a y for the second qubit, a z for the second qubit, and we get also tensor products of those. So for example, if I have something like x for the first qubit, tensor z for the second qubit, and we look at the matrix combination, then this is the 0, 1, 1, 0 matrix for the first qubit, tensor 1, 0, 0, minus 1 for the second qubit. And now the convention and how we turn this tensor product of two 2 by 2 matrices into a 4 by 4 matrix is that we multiply every element in this first matrix by the whole second matrix. So here this 0 will be multiplied by this whole second matrix, after which I get a 0 2 by 2 matrix. This 1 will be multiplied by this whole matrix, so I get a copy of this matrix. This one will be multiplied by this, so I get a copy of that matrix. And finally, this 0 will be multiplied by this whole matrix, so I get another 0 2 by 2 matrix. And so this operator, which is now for 2 qubits, X operator for qubit 1, Z operator for qubit 2, is now represented by a proper 4 by 4 matrix. When we were looking in the first cycle of these lectures at the Bell inequality and how it is violated by quantum mechanics, we were considering a particular 2 qubit state, which at the time was about polarized photons. So the labels were about horizontal and vertical polarizations, but now we have the labels 0 and 1. But the state that we were looking at had a ket for what we call the singlet, which in this notation would be the 1 over the square root of 2 of the 0, 1 minus the 1, 0 kets. And so the question is now, what is the 2 qubit analog of this single qubit statistical operator? Well, in this particular case, the operator will be the SS ket-bra. And so working it out like this, well, it's half of the 0, 1 ket minus the 1, 0 ket. So those are these tensor products that we have here, multiplied by the adjoint bra. So that's the 0, 1 bra minus the 1, 0 bra. Okay, so the ket bra of the singlet state with itself is this product, and that has 4 terms. So there's the first one, which is the 0, 1 ket with the 0, 1 bra. Then the second one is the second one, that's the 1, 0 ket and the 1, 0 bra. And then we have the 0, 1 ket with the 1, 0 bra, which is this product. And finally, we have the 1, 0 ket with the 0, 1 bra. And now let's remember that these are tensor products. So this is a tensor product of 0 and 0 for the first qubit and 1, 1 for the second qubit. So, but 0, 0 for the first qubit, well, that's just half of 1 plus a z. So this is half plus a z for the first qubit, and the 1, 1, well, that's 1 minus z. So it will be 1 minus z for the second qubit. And there's a tensor product between this operator for the first qubit and this operator for the second qubit. Then over here we have 1, 1 for the first qubit, and that's 1 minus z. And we have 0, 0 for the second qubit, so this will be 1 plus z. Looking here, we have 0, 1 for the first qubit. 0, 1 for the first qubit is x plus iy. So we have negative x plus iy for the first qubit tensor, and it's 1, 0 for the second qubit. 1, 0 for the second qubit is x minus iy for the second qubit. And the last term has just the roles interchanged. So the last term will be x minus iy and tensor x plus iy for the second qubit. And so now we have to collect the terms. So there is a identity half, identity half, identity half, identity half, which are added. So together we get half of a quarter, so another half, a quarter and a quarter of the identity tensor the identity. Okay? And then we have identity times z with a minus sign, identity times z with a plus sign. These terms cancel. Z tensor identity with a plus sign, z tensor identity with a minus sign. These terms cancel. Z tensor z with a minus sign, z tensor z with a minus sign. So these terms add. There's a quarter here, a quarter here. Together we have a half. A half of z tensor z. Now we turn to these terms. Here we have x tensor x with an overall minus sign, x tensor x with an overall minus sign, and a quarter here, a quarter here. So together this is a half of x tensor x. I look at y tensor y. Well, this comes with a minus sign and a negative I squared. So together overall it's a minus sign. And here again we have y tensor y with a negative minus sign and a negative I squared. So overall it's a minus sign. So a quarter here, a quarter here. These terms add also, and we get x tensor x and y tensor y. Now if we look at the terms which have x tensor y, well, this comes with a coefficient of plus I quarter here. X tensor y comes with a coefficient of a negative I quarter there. So those cancel. And the same for y tensor x, which has a coefficient of negative I quarter in this term, and the y tensor x has a coefficient of plus I quarter in the second term. So these cancel, and what we have in total is just this. And so there's a common factor of a quarter that I just pull out. And now let's see. So this is 1 tensor 1, but this is just the identity for the 2-qubit system. And then we have x tensor x plus y tensor y plus z tensor z. And just let me copy it like this. X tensor x minus y tensor y minus z tensor z. But now let's remember that this x is for the first qubit, this x is for the second qubit. So an alternative notation that is a little bit more helpful is to call this the product of x for the first qubit, x1, and this x for the second qubit, x2. And here we have y1 and y2. And here we have z1 and z2. And here we should understand that x1, for example, if we are finicky about the 2 qubits, is x for the first qubit and the identity for the second qubit. And the x2 that appears here is the identity for the first qubit and x for the second qubit. So remembering what we said about how this 2 by 2 matrix and this 2 by 2 matrix are combined in a tensor product of 2 by 2 matrices, this would just be the 0 matrix, and then the identity matrix, and the 0 matrix. And here we get the X matrix here and the X matrix here and the 0 matrix there. So in reading these products, we should think of these operators to be represented by 4 by 4 matrices, where the x1 is x for the first qubit, 1 for the second qubit. The y2, say, is identity for the first qubit, y operator for the second qubit, and so forth. Now this is very, very suggestive because x1, y1, z1, well, they should just make up the components of the sigma vector operator for the first qubit, and the x2, y2, z2 make up the sigma vector operator for the second qubit. So in the end, what we have is 1/4, 1 minus the full sigma vector operator for the first qubit, and then the dot product with the full sigma operator for the second qubit. And this now is a very compact way of understanding the singlet ket-bra in terms of the Pauli operators that refer to the two qubits. In summary, we use tensor products to construct 2-qubit kets from single-qubit kets. And we express the statistical operator for the singlet states in terms of the two sets of Pauli operators. In the next lecture, we continue to explore the 2-qubit state space.